Welcome back, science enthusiasts! Have you ever wondered what everything around us is made of? Quark, electron, neutrino, gluon, photon, bosons, Higgs boson. Have you heard of them? The answer lies in the realm of elementary particle physics and the remarkable framework known as the Standard Model of Particle Physics. Elementary particle physics is the branch of physics that delves into the tiniest building blocks of matter and the forces that govern their behavior. The Standard Model is like a map that guides us through the intricate world of particles and their interactions. Let's unlock the secrets of the subatomic world. In our last video, we explored the world of the four fundamental forces that shape our universe: gravity, electromagnetism, weak nuclear force, and strong nuclear force. Beyond the fundamental forces, let's now explore the particles that compose the matter in the universe. What exactly are elementary particles? They are the building blocks of matter. Imagine you zoom in on an atom, breaking it down into its core components. You'll find particles such as photons, neutrons, and electrons. But those are not the end of the story. Even smaller particles exist, aptly called elementary particles. Elementary particles are the fundamental entities that cannot be broken down further. They are like the alphabet of the universe, from which all matter and forces emerge. Here is a visual representation, a map of the Standard Model of Particle Physics. The Standard Model provides us with a comprehensive understanding of the fundamental particles that make up our universe, their properties such as mass, electric charge, and spin, a quantum property that determines the angular momentum of the particle and the intricate interactions between them. This table reveals the incredible diversity of particles and their properties. Don't worry, it's not as intimidating as it might seem. Let's take a look. We'll start with a basic categorization of these particles. Elementary particles can be classified into two categories: fermions and bosons. To better comprehend these cosmic threads, let's explore these two primary families of elementary particles. At the heart of matter, we have fermions, which are the fundamental building blocks of the universe, including quarks and leptons. Bosons, on the other hand, are responsible for transmitting forces between particles. We will analyze them soon after fermions. Quarks play a vital role in the structure of matter. Quarks, with their enchanting flavors, interweave to form protons and neutrons, which constitute the nucleus of atoms. Quarks are unique in that they possess a property known as color charge, which is associated with a strong nuclear force. In quantum chronodynamics (QCD), the theory that deals with a strong force, there are three types of charge referred to as color charge. This analogy draws from the three primary colors, red, blue, and green, RBG respectively, that humans perceive. However, it's important to note that the term color in this context is metaphorical and doesn't refer to the colors we perceive in everyday life. Instead, it is used to describe the strong interaction between quarks. Quarks have a spin of 1/2. There are 6 known types or flavors of quarks: up, down, charm, strange, top, and bottom. The top quark is the heaviest known quark. The up and down quarks, which are the lightest among the 6 flavors, form the building blocks of ordinary matter. Each quark flavor carries a fractional electric charge. The up, charm, and top quarks have a charge of +2/3 elementary unit, while the down, strange, and bottom quarks have a charge of -1/3 elementary unit. This fractional charge has not been observed freely in nature, as quarks are never found alone in nature due to a phenomenon known as confinement. Instead, quarks are always bound together in composite particles called hadrons. Hadrons can be either baryons, which consist of 3 quarks, or mesons, which consist of a quark and an antiquark. The most common baryons are protons and neutrons, which are composed of up and down quarks. Protons consist of 2 up quarks and 1 down quark, while neutrons consist of 1 up quark and 2 down quarks. These baryons are found in the nuclei of atoms and are responsible for the stability and structure of matter. The charge of protons +1 arises from the combination of 2 up quarks +2/3 each and 1 down quark -1/3, while the charge of neutrons, 0, results from the combination of 1 up quark +2/3 and 2 down quarks -1/3 each. The charge of a proton can be represented by the following equation. Similarly, the charge of a neutron can be represented by the following equation. The experimental evidence for quarks emerged in the 1960s and 1970s through high-energy particle collision experiments, which provided strong support for the quark model. Quarks are also subject to the strong nuclear force, which is carried by particles called gluons. Gluons mediate the interaction between quarks, holding them together within hadrons. Leptons, on the other hand, are another crucial category of particles. They include electrons, muons, and taufs, along with their corresponding neutrinos. Electrons, the negatively charged particles, orbit around atomic nuclei, forming the outer shells of atoms. They play a vital role in chemical reactions and the formation of molecules. The interactions between electrons and atomic nuclei are responsible for the diverse properties of matter, such as conductivity, magnetism, and the behavior of materials in different environments. Electrons are the familiar particles responsible for electricity and chemical bonding. When a voltage is applied, electrons can flow through conductive materials, creating an electric current. This flow of electrons is the basis for many technological applications such as electricity generation, electronic devices, and information processing. One remarkable property of electrons is their tiny mass. Compared to other particles in the Standard Model, electrons have one of the smallest masses. However, their small size and mass don't diminish their significance in shaping the macroscopic world we experience. Electrons have a spin of 1/2. Neutrinos are electrically neutral, meaning they carry no electric charge. They are extremely elusive and interact only very weakly with other particles, making them notoriously difficult to detect. There are 3 known types or flavors of neutrinos: the electron neutrino, the muon neutrino, and the tauf neutrino. Each flavor is associated with a corresponding charged lepton, the electron, the muon, and the tauf respectively. Neutrinos are created in various processes such as nuclear reactions in the Sun, radioactive decays, and high-energy particle collisions. They are abundantly produced in these astrophysical and terrestrial sources. One intriguing characteristic of neutrinos is their ability to change or oscillate between different flavors as they travel through space. This phenomenon, known as neutrino oscillation, was a groundbreaking discovery that proved neutrinos have mass. Bosons are responsible for transmitting forces between particles. As we learned, there are 4 fundamental forces that govern the interactions between particles. To recap, we have the electromagnetic force responsible for interactions between electrically charged particles, the strong nuclear force binding quarks within protons and neutrons, the weak nuclear force involved in radioactive decays, and finally gravity, the cosmic force that governs the motion of celestial bodies and shapes the large-scale structure of the universe. Let's delve deeper into each category and the particles associated with them. The electromagnetic force, responsible for interactions between electrically charged particles, is carried by photons. Photons are massless particles that travel at the speed of light, allowing them to effortlessly traverse vast distances. They enable the transmission of light, the electromagnetic waves, and the entire spectrum of radiation that surrounds us. Moving on to the strong nuclear force, which binds quarks within protons and neutrons, the primary mediator is the gluon. Gluons come in various types and colors, acting as the glue that holds quarks together within atomic nuclei. Their interactions contribute to the stability and structure of matter as we know it. Next, we have the weak nuclear force involved in radioactive decays and interactions within the atomic nucleus. The W and Z bosons play a vital role in mediating this force. These particles are relatively massive compared to photons and gluons, and their interactions shape the dynamics of nuclear processes such as beta decay. We've already discussed 3 of the 4 fundamental forces, but what about the force, you might be wondering? While the other 4 fundamental forces have known particles mediating them, gravity is still a mystery in this regard. Well, that brings us to an intriguing and hypothetical particle called the graviton that could potentially mediate gravity. The graviton remains a theoretical construct yet to be directly observed or confirmed. It's believed to be massless and spinning too. Scientists are actively engaged in research and experiments to unravel the mysteries of gravity at a quantum level. They are actively exploring various approaches, including experiments at particle accelerators and investigations into the nature of gravitational waves in hopes of detecting or finding indirect evidence of the graviton. The nature of gravity represents unique challenges when it comes to experimental verification. Gravity is an incredibly weak force compared to the other fundamental forces, making it difficult to directly observe or measure gravitons. Additionally, the scale at which the effects of gravity become significant, such as the realm of quantum gravity, remains a complex and open area of research. The search for the graviton takes us deeper into unifying all fundamental forces into a single elegant theory. Let's now see the Higgs boson and delve into its remarkable properties and significance within the realm of particle physics. The Higgs boson was first theorized in the 1960s by physicist Peter Higgs and other researchers, and its existence was experimentally confirmed in 2012 by the experiments at the Large Hadron Collider (LHC). The Higgs boson plays a crucial role in the mechanism of electroweak symmetry breaking, which explains how elementary particles acquire mass. According to the theory, a field called the Higgs field permeates all of space. Interactions between particles and this field give rise to the mass of particles. The Higgs field is characterized by a scalar particle known as the Higgs boson. It is the quantum excitation of the Higgs field and is responsible for mediating the interactions that give mass to other particles. The discovery of the Higgs boson was a significant milestone in particle physics, as it confirmed the existence of the Higgs field and provided insights into the mechanism of mass generation in the universe. The Higgs particle is electrically neutral and has a spin of 0, which makes it a boson. The Higgs boson is the only fundamental particle with no spin. Its mass was measured to be around 125 GeV by the experiments at the LHC. the production of the Higgs boson in particle colliders such as the LHC involves high-energy collisions of protons. These collisions release a tremendous amount of energy, allowing the creation and detection of the elusive Higgs boson. Studying the properties and interaction of the Higgs boson is crucial for further understanding the fundamental forces and particles of nature. It helps to shed light on the origin of mass, the nature of the Higgs field, and the possible existence of new physics beyond the Standard Model. The experimental discovery of the Higgs boson has opened up new avenues of research in particle physics and has deepened our understanding of the fundamental nature of the universe. It represents a significant achievement in the quest to unravel the mysteries of the subatomic world. To summarize, the world of particles is rich and diverse. Fermions are the fundamental building blocks of the universe, including quarks and leptons. Quarks, with their different flavors, combine to form the protons and neutrons that constitute atomic nuclei. Leptons, such as electrons and neutrinos, play an essential role in the behavior of matter, facilitating chemical reactions and bringing balance to the fundamental forces. Bosons, on the other hand, are the messengers of the forces that bind and shape the universe. Photons, the ambassadors of light and electromagnetism, illuminate our world. Gluons glue quarks together with a strong nuclear force, while W and Z bosons facilitate the enigmatic realm of weak nuclear interactions. The Higgs boson is responsible for endowing other particles with mass and plays a crucial role in the mechanism of electroweak symmetry breaking. The Standard Model of particle physics can be characterized as a comprehensive theoretical framework that describes the fundamental particles and their interactions. It provides a systematic understanding of the building blocks of matter and the forces that govern their behavior. The model combines quantum mechanics and special relativity to explain the electromagnetic, weak and strong nuclear forces. It successfully accounts for a wide range of experimental observations and has been extensively tested through experiments conducted at particle accelerators worldwide. The Standard Model is regarded as one of the most successful theories in physics, providing a solid foundation for our understanding of the subatomic world. However, it is worth noting that the model is not complete and leaves unanswered questions such as the nature of dark matter, dark energy, and the unification of forces, without including a description of gravitational interactions. As we continue to explore the mysteries of particle physics, we unlock the secrets of the subatomic world and gain a deeper appreciation for the intricate beauty and complexity that underlies our universe. The Standard Model serves as a guide in this fascinating journey, but there are still many questions to be answered and discoveries to be made. Additionally, it's important to mention the existence of antimatter, which consists of particles that have the same mass as their corresponding particles but opposite electric charge. Antiparticles, such as antiprotons and positrons, the positive electrons, provide valuable insights into particle interactions and the symmetries of nature. We will delve deeper into the intriguing world of antimatter in a later video, where we will explore its properties, interactions, and its role in our understanding of the universe. Thank you for watching this video about the Standard Model. Stay tuned for future videos where we will explore more topics and mysteries of particle physics. We appreciate your support and look forward to seeing you in the next video.